Yeah, I tried to, believe me, I don't know if that's right or not. I know that's right. I guess that's right. You know, you have these translators and you use them, they're on the computer, who knows? I live in Pensacola, Florida, which is right up here, right in the northwest corner of Florida. How many people have been to Florida? But all Orlando, right? Miami. Okay, so that's where Florida is. We just had a big hurricane go that way. I'm showing you some pictures of the hurricane that hit us in 2004. That's a picture of my backyard when the weather is good. And this is a picture of my dock, which is paradise most of the time. But the other 2 days, not so hot. So this is a picture of the inside of my house after the hurricane in 2004. Just to get an idea, I mean, when you live in a hurricane-prone zone, this is the risk we have. So I've been retired for a while. I now work at the University of Melbourne in Australia every year. Melbourne is down here in the southern part of Australia. This is Tasmania. I was showing a few pictures of that. This is where you catch in Melbourne. If you're Japanese, are there Japanese people here? If you're Japanese, of course, you eat every part of this, but I was not interested in doing that. But that's fun catching it. And the other place I work is at the University of Missouri with Jim Keller. Here's a picture of Jim and I in Hawaii with some fish in the water. You don't catch these fish here. Okay, I hope. Okay, does that make any sense to you? Yeah? Yes? No? Today in the United States is Halloween. The second biggest holiday of the year in the United States, actually. Now, Christmas is the only holiday that's bigger than Halloween. And Halloween is it's my favorite holiday, and this is a pumpkin that I carved a few years ago. So I just put that in there. Notice in Cyprus, there is no Halloween, right?
So, I was celebrating.
I thought about coming in an outfit. That would be too scary. Okay, here we go. So, I had no idea how many people know about clustering, so I put some charts in the front of this talk that I don't usually give about clustering, just to give you the idea about clustering, what it's all about. I have a nice history of visual clustering, and I'm going to talk about 4 algorithms that I've had a hand in. VAT, iVAT, there's actually a asiVAT now, SVAT, and scalable VAT, and POVAT for rectangular data. I'm really going to try to get through all of them today. I guess I was promised 75 minutes. I'm going to try to make it 75 minutes. We'll see what happens. Okay, so the first question is, what are clusters? So if you look up the word cluster in Google, if you look up on the internet, this is the first thing you will find. Cluster is a grouping of a number of similar things. And if you look up the World Dictionary definition, cluster means, this is a verb now, to gather into or form a small group. But if you look at the online dictionary, a group of similar elements closely together. So the point is, there are 3 ingredients to what humans think of as clusters. They're groups of things that are similar and close. Okay, so basically, this is the way we also think about clusters when we talk about clusters of data. So humans, we use this in a naive way, and we all think we understand what it means. I'm going to show you in just a second that it won't agree with each other what it means. We'll see. People often disagree about clusters, so why should computers do any better? So what do humans see in a cluster of objects? Is this a cluster? Yes? Is this? Really? I just said it's a group of things. By that definition, this cannot be a cluster. A single thing cannot be a cluster. Is this? This is one cluster, maybe with some kind of noise. This is some sort of anomaly, but I would not regard this as a set. It's an interesting point in the data set, but I would not regard this as a cluster. we see a group of things. Is this a cluster? Is this? This is the same set of points as that, but it's just blown up. Right? So you see, we need to see closeness, physical closeness. Of course, the computer needs to see it in the data set. What about this? Two clusters of birds, yes? Two clusters of birds or one cluster of birds? Well, this is a set of objects that you would give two physical labels to, but there's only one cluster here. It's often the case that people trick themselves into thinking they should look for, given data that represents a set like this, they should look for two clusters. But from the computer's point of view, from the human point of view, there's only one cluster here. It's just, the objects are mixed together. What about now? One cluster of birds, one cluster of chickens. Well, certainly it's one cluster of chickens with one noise point. How about this? Coin flips. 1, 2, or 3 clusters. Now, pretty interesting, isn't it? I'm sure that in the room here we would have many different opinions about what to call these things we're looking at. Some different opinions anyway. Okay, well, there can't be 8 clusters because I said there had to be at least two things in a cluster, right? The point is, humans are presented with sets of objects that have properties like these, and we with our infinite ability for pattern recognition, can recognize similarity, we can recognize closeness, and we can recognize separation. So that's my little naive, intuitive idea about clustering. This is one of my grandchildren. You see, the apple never falls far from the tree. Okay, so what are clusters to computers? Well, there are 3 problems in clustering with numerical data. First, we can talk about assessment, and actually, this is the problem that I'm here to talk about today, is does the data have clusters? Secondly, once you decide to look for clusters, you have to find a partition that's capital U with C clusters in it in data set X or R. I put this quote up here, you'll see as the talk goes on, and I like quotes a lot. This is a quote that I took out of a book written by Robert Tryon, published in 1939, correlation blah, 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 which is said to comprise a cluster. And the reason I put this quote up here is because I believe this is the first person that used the term cluster analysis. I'm not 100% sure, but I've never been able to find an earlier reference to the term cluster analysis than this. And I have this book hard to find, but I have it here on my computer if you want to get that. And then the third problem is, once you have clusters or partitions, do you believe it? Are they any good? After all, every clustering algorithm areas will produce clusters. That's its job. Right? No matter what, whether the data has clusters or not, whether you look for the right number or not, you will get clusters. Every clustering algorithm is guaranteed to produce them. So you have the problem of validation, and that's clearly the most difficult of the 3 problems. Is a different quote from a very early paper by Thorndike. Now we're faced with much nastier problem of determining appropriate value for C. C is the number of clusters. Okay, so humans can't see clusters of objects, and the question is how can we make a computer see clusters of objects? Well, we use numerical data, of course, 2 kinds of data, object data and relational data. And this is my definition of cluster analysis. It's a bunch of computational models and algorithms that search for groups of similar data that are close. So basically, in clustering, we're simply searching for structuring data. We hope that a clustering analysis program, which can only produce algorithmic clusters, think that any clustering algorithm would be able to find these three groups of data. You would think that. And if you run hard C means, HCAM stands for hard C mean, on this data set, you get the right answer, provided you're told to look for 3 clusters. But if you're told to look for 2 clusters, it will find 2. If you're told to look for 6 clusters, it will find 6. Now here's something that may surprise you. The initialization is very important in most of these algorithms. Here's an initialization problem. How many people have seen this photo? Okay, then you have to shut up. How many people haven't seen it can see anything in it? Can you see any kind of maybe not, but if I say the word dog, can you see the dog now? This is an old example of how important initialization is. As soon as someone says dog, you can see it's what we call a combination. I saw this photo when I was a graduate student, before most of you were born. And I just put it up to show you how easy it is to not see what seems to be obvious if you're not initialized correctly. Let's see what happens here. RC means on the same data set. Lucy Conchiva visited me about 15 years ago now. She just stumbled onto this by accident, this example. It's a great example, though. For one initialization of hard C means, you get this solution, and for a different initialization, C equals 2, you get a different solution. Which is, that should bother you a little. For C equals 4, the same thing happened. 2 different initializations produce 2 different solutions, the same problem, and all 4 solutions are wrong. Right? And now imagine if this data was not in R2, but it was in R4. Then you couldn't see it with your eyes, and you would have no way to decide which of the solutions you have is a good solution. That tells you that validation is one of the most important problems that you can work on. Because you can generate partitions forever with these algorithms, and you have 100-dimensional data, you have no idea if any of them are. So you should bear this in mind as you move on in your career to cluster. What about parameters? So there are problems with parameters. So here's a data set, deck of cards. Well, the decks of cards in Cyprus at 52. I don't know. 52, I guess. How many cards? Oh, this is a data set. It says 52 cards. How many cards are there? Well, C is 52. How many ranks? C equals 13. How many suits? C is 4. Colors usually, C is equal to 2. How many decks? C is equal to 1. So here we have a fixed data set, and we have 5 different correct numbers of clusters for this data set. So the point is, the number of clusters across C depends to some extent, to a large extent, on the question you ask of the data. Right? So you have a data set, you send it in, and you have something in mind you want to answer. For that question you have in mind, the answer may be C equals 6. But if you ask a different question, the right answer might be C equals 4. This is an important point that a lot of people miss. All right? The question you ask of the data, to some extent, determines what can be right and wrong. Okay, here's a different example. Here's a set of 4 objects. I just made this example up so you can see. It's easy to fix it up this way. If I ask you how are the objects related to each other, there's one cluster. By age and sex, there are 4 singletons. They're not really clusters, there are 4 singletons. If I go by blood type, I can fix it up so that there are 3 clusters, and there are lots of different correct answers. And if the question is sex, then there are 2 clusters. The question is eye color, there are 2 clusters. The question is parent or child, there are 2 clusters. And again, the number of clusters even within C depends on the question you ask of the data. So these are important points about clustering that you need to bear in mind. Okay, a couple of technical charts here. We're not going to have, I almost took these out, but I realized that right after this I do use U, the partition maker, so I left them in. Just try to keep going. So this is a picture of the standard 4 kinds of label vectors that we have. I can only make the picture for C equals 3. The crisp is 3 red vertices, vertices, they're what we call the crisp vertices. Crisp is not soft, hard. In engineering, we sometimes call these I, J, and K instead of E1, 2, and 3. So I was an engineer. By the way, I have a degree in engineering. And back then, they called them I, J, and K. They still use it for these three vectors. I, J, and K. If you take the convex hull of those 3 points, you get this triangle. It's a piece of a hyperplane. And the vectors that lie on this triangle are fuzzy or probabilistic label vectors, and they look like this point right here, y. The entries between 0 and 1 that sum to 1. Could be fuzzy, could be probabilistic. An infinite number of them, obviously. And finally, we have the possibilistic label vectors. Here are just green unit cube here. So here's an example of a possibilistic label vector. Entries between 0 and 1, but they sum to less equal to C. So there's 4 kinds of labels that we can produce clusters with. Representation by partition matrices. This is the most convenient way to represent partition. So there's a C by N, C clusters by N objects. So the ith row gives the membership of all the objects in cluster I, and the kth column gives the membership of just object K in all C clusters. So why is validating U hard? Let's have a look at fuzzy C mean. I'm not going to really talk about fuzzy C means today. This is the only chart I have about it. Fuzzy C means is a function of the input data, X, the number of clusters C, a weighting exponent M, a termination threshold epsilon, a termination cutoff criteria T, and 2 norms, and a set of prototypes. So, how many choices do you have for each of these parameters? Here's the answer to each one. The number of possible partitions from fuzzy C means that many, which is a lot, right? So the point is you can generate partitions forever and never, and really forever, and have only a small fraction of partitions you could look for. This is why validating U is hard. So please remember this, if you're interested in clustering, this is important. We can't say the IRS data has 2 clusters, CPOV means computer point of view. We cannot say that, all right? We have to specify a model and an algorithm. And once we do that, we can say it. We can say that the IRS data has 2 fuzzy C means clusters when fuzzy C means is optimized by alternating optimization. We could say that. Or, for example, we could say the IRS data has 3 clusters found by the EM algorithm when it's optimized with GA. Okay, you get the point? The point here is in this chart, which has a bunch of levels. So what are these levels? There are many clustering models here. And for each clustering model, there may be a dozen different algorithms. Just for this clustering model here, there may be a dozen algorithms that are different ways to optimize it. For a fixed model, it's true for fuzzy C means, and with fuzzy C means you can use alternating optimization, GA, there's various kinds of programming approaches, PSO. So the point is there are different algorithms. And for each of these choices of a clustering model and algorithm, there are a lot of parameters you could choose. We just saw in the last chart, different parameters for fuzzy C mean. And once you make all those choices, you can generate a bunch of partitions, right? Just coming down this left side. So you end up with a whole bunch of candidate partitions. These are the candidates that you have. And enter cluster validity. Cluster validity of choose the U that you generated. So this is a chart that really summarizes what happens in clustering. And the first sentence, the first statement is the most important statement. You will read, and I have written hundreds of times, things like that are really technically somewhat wrong. I've often said the IRS data is 2 clusters. I believe it only has 2 clusters, but I believe it for most models it only has 2 clusters. Well, I can produce 3 clusters in the RSA if I choose the right model. So, does it have 2 or 3? It depends on the computer program you use. From the human point of view, we'll never know because it's just 4E. Okay, there's, I don't know how I'm doing for time. Is there a way to tell? If you get sick of this, just get up and leave. I'm used to that. Well, you know, I'm locked in to try to finish it now. This is, to me, this is a really interesting part of this talk. So visual arrangements of objects, they go back much further than 124 years, I'm sure, but I have this paper by Petrie here on my computer, and Petrie suggested, he was an archaeologist, suggested that the order of events is the main ingredient of history itself. And he described the order of events in terms of sequence dates. We're going to see in just on the next chart, he arranged 917 pieces of prehistoric Egyptian pottery from over 4,000 overlapping graves based on a set of 100 sequence dates. You'll see what that means in just a minute. And I just copied this out of his paper. This is just to show you that he did talk about it, right? Next, place these as far as possible in the original order. The original means in, historical sequence. And so he gave these 5 methods for doing that. And notice, for example, number 3, statistical grouping by proportionate resemblance. Basic for classifying large groups. So bear in mind now, this is 1899. Here I have some, these are the actual dates, 5400 BC to 4800 BC. And then over here is this older than newer, so we'll see what these sequence dates here. So here's some ceramics. I just copied these out of the paper. So the numbers up here on the right side are his sequence dates. So he just divided the scale of 600 years into 100 slices, right? And then he tried to arrange the pottery so that it went in sequence. And just so this is the whole point. So I had to show these to you. I think there were 3 ceramics, 1 slate, 1 flint. No, the whole point is this is visual clustering. It's exactly visual clustering. But there's no, there's no numbers really attached to it. There's no computation, obviously, or anything else. So humans are good at this and have done it for many years. But for us, visual clustering is a little more technical. We like to look for graphical representations and numerical data. So there are 2 ideas involved here, 2 ways to go about it. If I have vectors for my data, vectors that live in RP, so RP may be 100 or 100. I try to picture them in R2. The standard sort of thing that we think about, R2 or R3, is like Salmon's projection or pursuit projection, something like that. Mental components analysis, where you project data in R10 down to R2, and then you look at it with your eye, you try to decide what's in it. Right? We're not going to look at that today because it's on the right, we have a much more interesting situation. Here's a relation matrix that's m by n. It's not necessarily square. And I've made the rows of this red and blue just to indicate that it might be the case that some of the rows are more related to each other than they are to the other rows. And you're going to see in just a second, right? I just made this graph up so you can see. So the 2 blue rows look somewhat similar and the 2 red rows look somewhat similar. What you're trying to do is with your eyes, try to get a picture of what this data represents. And that's the whole rest of this talk, that's all we're trying to do. We're not going to find any clusters. We're going to try to decide what's in data by looking with our eyes at actual images. So because this situation is a little more general than that situation, this is a better problem to study, and it's a more natural problem from the point of view of the technology. So here are some visual methods that have been around for a long time. I don't know if you know this. I was shocked to learn that Carl Pearson invented a histogram. Did you know that, Marios?
Yeah,
Carl Pearson is a British statistician.
Mm-hmm.
And Ronald Fisher's most famous opponent. And he invented principal components analysis. I was really surprised to learn that. He was a really smart, a minute. And this is just a sample. I mean, there are hundreds and hundreds of methods to do this. To try to look at high-dimensional data with some sort of low-dimensional view. So here's the radar plot. You all have the program that will produce on your computer, plot on your phone. Radar plots have been around for a long, long time. You saw them in the previous chart. And I just happened to stumble on this next chart I'm going to show you. It was published just a few months ago in Time magazine. But you'll see right away what it's all about. You just look at it without understanding what the chart is. If I say arrange these in clusters, you would do it, right? You would take all these kind of big blocky red ones and put them together with your eye and so forth and so on. You can see there are 5 colors here. So the guy who drew this decided there were basically 5 clusters in his data. The reason they're not assembled in clusters is this is done alphabetically by states in the United States. Alabama left, and so you can find your state easily. And what are these? What are these things? Well, look at this in Utah, for example. So this is taxes. And Utah is a state that has fairly low taxes. There are 4 coordinates: corporate, individual, sales, and property taxes. All right, so the vector that would represent Utah is this vector right here. You just plot, you just make a radar plot, right, and that's it. That's how it builds. And if you live in New Jersey, God forbid that you live in New Jersey. How many people been to New Jersey? Yeah, but you're here, right? New Jersey would be a bad place to be right now, actually. If you live in New Jersey, look good. I mean, this, you're going number 50 in all 4 coordinates. So they have 5 passes in all 4 coordinates. This is a radar plot. It's simple to understand. It's very, you know, if you have a, when is it useful? Like, well, I've always called the method stars. To use color to use shape, it's useful if you have a small number of objects and a small dimension, right? If these vectors are, I mean, if these vectors are in R50, right, the stars are just, you have so many coordinates. On the other hand, if there are 1,000 of them, you just go Google it trying to see what's there. This is a useful method for small data sets where you just have a few dimensions. But there are many methods like this, and they are useful if you have, many people do deal with small data sets. This is the way to look at it. So, I talked about Tryon. This is out of his book. This is actually the basis of his entire book. His wife collected this data. She was a professor at Berkeley in communications. He was a professor in psychology. This is a set of 20 personality traits in 170 12-year-old boys. I can hardly think of a worse test group than that. And these were correlation coefficients. You'll see in a minute what these 20 traits are. And there was nothing on the diagonal because they didn't ask the boys to rate themselves. So trying just to make this, to complete this matrix, try and just put the max in each row onto the diagonal. And he did this. He said, okay, we'll just plot the rows of the matrix, and this is what it looked like. Not what it looked like for him, I'm sure. Select the row in the row among these, you know, the row in the data with the largest row sum. It happened to be J. It's hard to see there. But here it is J. Happens to be J. And then what do you do? Well, you just start grabbing these graphs and matching them with your eyes. Right? I can imagine that Tryon and his wife have, no, that's probably not true. Tryon's graduate students probably, right? They spread these graphs out and they arrange them and all. And when they were done, they called the professor in. He said, yeah, that's okay. That's probably what happened. Right? You guys all know how that works, I'm sure. Anyway, something like that happened. And this is what, this comes out of Tryon's book. Actually, these, I just Xerox this right out of his book. These are the 5 clusters that he found. So this cluster they came up here, FBU, these are boys that get in fights, they're bossy, and they're unkempt. Right? Close them together. And these are boys that try to get attention, they're restless, they're talkative, and so forth. So there were a few boys, there were a few graphs that didn't get in there. Anyway, this is visual clustering. Right? Not only that, look at this. These heavy lines aren't points in the data, they're the mean profile of the set of graphs in the data. So these are basically prototypes. And right here in 1939, you have a prototype, you have the basis So here's a little 5x5 matrix D, and if you just run it into MATLAB, you get this image right here. And the question is, does this image tell you anything about the, does this image tell you anything about the structure in this data set? And the answer is, well, I couldn't say there is any structure in the data set, I guess. And the fact is, we will see on the next chart, if I just reorder the rows and columns of D, I will see some structure. So here is the reordered version of D. It's known as VAT, Visual Assessment of Tendency. That's, I'm going to tell you what that is in a minute. There are many, many, many reordering schemes, not just mine, all right? Many, as I'll tell you about in a little while. But if you just reorder, you get an image like this, and this image is pretty clear in its implication. It suggests that these dark plots along the diagonal suggest that the group of objects that are put together in these dark plots are more related to each other than they are to the objects in other plots. And that's the whole idea of the whole rest of this talk, is to try to think of schemes that you can use to look at data in any number of dimensions, all right, and get visual ideas about what's in the data. That's the whole idea. So there are three functions that affect the displays that you see. The first one is how you depict the values individually. We saw graphs, here's the images. We saw Petrie's just laid them out on a blanket. Second, how you reorder the rows and columns to highlight the structure. As I said, there are many ways to do that. And lastly, I don't have a partition of these 5 objects. I have a suggestion that I could partition into 5 objects. So the third question is how do I actually get the partition? Okay, so here's the early history of visual methods for relational data. Started, as far as I can tell, in 1873. I've got Lewis' image, you can see on the next chart. In fact, I have, except for this one, I have all of these papers on my computer, and I have some examples from some of them for right now. So here's the first rectangular image, relational data. Lewis did a study of 20 neighborhoods in Paris, and there were a bunch of demographic variables, like how much beer they drink, how much wine they drink, how many baguettes they buy, that kind of stuff. And he made this chart and colored it himself manually, I'm sure. There wasn't any other choice, just to see if he could see structure in the data. He did not think of or try to reorder the rows and columns to enhance the structure that might be in the data. I'm just going to turn the data I have into an image and look at it and see if I can see anything. And I think this is the earliest, anyways, the earliest one I know of. Social statistics in Paris. That's a scary statement. I believe the first reordered dissimilarity image was, she's 102 years old now. Zakhanowski, it's this image right here, and you can see creeping in these 2 dark blocks. Creeping in, and I have a photo here plugged in and tell how it does it. Blobs, very small size. Okay. This again was all done by hand. And I was pretty surprised to find it. As you'll see later, I was really pretty surprised. In 1944, actually I think there's a 1940 paper which I believe has an image like this, but I've never been able to get that paper by person in Perth. But I have this 1944 paper by Cattell, and this image is from it. And this is a great paper for the following reason. This is a really nice, where's that thing? You told me I should use it. I'm never any good at this laser view. And it doesn't work anyway. Look at this. That's without single linkage. One of the reasons I put this quote up here is I believe this is where the term single linkage started. Well, everybody in the room knows about single linkage, right? Does anybody in the room know about single linkage? How many people know about single linkage? I should give a different talk. Tomorrow I can tell you about single linkage if you want to know. Anyway, it's single linkage age is probably the most well-known as a relational, non-fuzzy relational clustering method. It's been around, as you can see, forever. And look at what it tells us. It manipulates the order of the variable in an attempt to bring alongside the diagonal. If the process is successful, the result of clustering is clearly and strikingly recorded as in this diagram. So this 1944 has it all right here. And when I found this out, I was completely and totally shocked. Yeah? Because, as you're going to see, 56, 58 years later, being halfway wrote a paper, we didn't even know about this paper then. We said, hey, we just invented this method. So here's Peter Steve, he's still alive. I still correspond with Peter, he's in the UK. This comes out of a 1957 paper. Notice the journal, microbiology. Nowadays they call it bioinformatics. Right? But back in those days it was just called numerical taxonomy. And Peter produced this thing with computer generated dissimilarity. But the image was still drawn by hand. 7 clusters, which is small clusters down here. Shortly thereafter, Floodgate Hayes produced this image in their paper. All right, the reason I put it is the first article on computer-generated single linkage clusters. Again, though, this image was drawn manually. Now comes Robert Ling. Robert Ling, I knew him well. I got data from Robert when he graduated just before I did. He was a student of John Harkins at Yale. And I read his PhD thesis, which I think he turned in 71. I had this algorithm in it. I got some data from him for my PhD thesis. So I can't say I didn't know about Robert's method named shade. But let me just tell you a little bit about it, because I think it's a really, historically anyway, it's a really important paper. So obviously the principle used, the representation elements, blah, 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 computer printed characters and various shades of darkness. And then the computer characters or the symbols are down here. Okay? So the way Ling made the computer make this image was to make the printer do overstrikes. Now, how many people in the room know what an overstrike is? Does anybody in the room know what it is? God, I'm so old. Okay, did you ever see a typewriter that had the arm came up and hit the ribbon, and right? You see those, right? Okay, so in this day, 1974, the printers for the computers, but they had little balls on them, and they traveled across just like a typewriter, right? And there would be a card that says, print this symbol right here, and the ball would hit it, right? And then it would advance the carriage one stroke, and it said, print this symbol, and the ball would hit, and so forth and so on. So that's the way printers in those days weren't big decks of cards, of course, and all some of them with that in a minute. So the way Ling made these images was this. He would say, print this symbol in this IJ, in the IJ location in this image, digital image, and it would say, back up and print this symbol over it. And you would get, equals and plus together, and it would make a shade of darkness that was different than any of these basic shades. This is like his alphabet for intensities, and with it he could construct, language of intensity. Yeah, we all did this. But he thought of making, you're going to see his image, he thought of doing it. Here it is coming, here's the iris data. Everybody's familiar with it, right? Some people are familiar with it. This is a picture of features 3 and 4. There's 150 points in the iris data for features, 3 physically labeled subspecies, but most clustering programs think there are 2 clusters. Anyway, Bob Ling only used 99 points. I never did ask Bob Ling. He was close to me. He worked at Clemson his whole career. But I never asked him why I only used 99. But my conjecture is he used 99 because there were only 99 columns in the computer card. They couldn't print anything in column number 100. So this is the biggest image you could make. So this is without the order, and this is with the order. And this is computer generated now, this image. And I believe this is the first computer generated image ever. funny. How many people in here have ever heard of Fortran? How about decks of cards? Yeah, when I was a graduate, when I was an undergraduate student, I used to go to the printer. You had to, every card, if you want to make an alpha in column 16, you had to punch a card, right? In the wintertime in Cornell, it's snowy, it's icy, like you're walking across Cornell, you're like this, hoping you're gonna slip, because you had this big box of cards, right? And if you slip and scatter them, forget about it. You throw them away and make a new set. So, you guys don't realize how, maybe you do realize how much has happened in the last 25 or 30, 40 years, a lot. And the growth of technology, you guys grew up with smartphones and stuff, I'm still trying to figure out how vinyl records work. How many people know what vinyl records are? And we finally come to the first algorithm. So, Rick Hathaway and I wrote this paper in 2002, making the following claim: the utility of the image of a matrix D for visual assessment cluster depends on the ordering of D. Yeah, and our idea was to reorder it, so yeah, like duh. And this is an example of what I call the shelf life theorem. Okay, we can talk about that later. The important point is, you can see this and they're just laughing. How many people know who this is? Anybody? Okay, here's a quote that you need to bury in your brain. It's the Hegel paradox, and it's about as true as you could possibly get. All right? Man learns from history that man learns from nothing. And of course, it's related to Hathaway and I learning nothing from the history of this topic. And I have no excuse because I know about Lane's work for 30 years ahead. You get caught up in something and you don't go backwards in time and try to take care of everything. And now it's impossible anyway. I mean, there's so much stuff out there it's impossible to cover your bases. You should try. So here we go. Oh. So here's the first paper. This is Rick Hathaway. He's at Georgia Southern. Jackie Hoopan was at University of West Florida. Great hat. Yeah, she's cute too. And she's now at the University of Virginia. Then later on, these people were all from Australia, or Dale Long is known in Beijing, but he was in Australia when I met him. Just like he is in Australia. Rao was in Australia. Bill wrote some papers and we're still working. Tim Davis was a late comer, he's a bass player, a really good bass player. Him and I are still working on this problem and still posting papers about it. So let me back up here. I have these papers all set to transfer to your flash if you want them, PDF form. Okay, so that family tree. It's like how many people know what a cottage industry is? Ever heard that term, cottage industry? Cottage industry. As opposed, it's where grandma sits around and makes pita bread in her kitchen and sells them one at a time, as opposed to the big bakery down the street, which is real industry. Right? So that thing has become a cottage industry for me. It's every one of these boxes of paper or two, spread over 10 years. Anyway, you're going to see a few of these. So here's the algorithm. I'm just going to flash it up. Don't bother trying. It's really simple to understand this. I'm going to tell you how it works. What did that do? That's when I decided we were just building. In comes the data set D. It's a symmetric square matrix. The dissimilarity is usually distances. We just get the minimal spanning tree of the data. Only we do it by starting at the longest edge. You know, when you do Primer Crustal's minimal spanning tree, you just start anywhere. And if there is a minimal spanning tree, you get it. All right? There's a reason we start at a long edge, which I'm not going to discuss today. But anyway, that's one small difference with Primer Crustal's algorithm. And you just go through, build a minimal spanning tree. Well, we don't want the tree. What we want known as the indices. The order in which the edges come into the tree. That's the thing that we will use to reorder. See, this is the array of indices that come into the middle spanning tree. We just reorder the matrix D that way. Alright? And we don't take clusters out of the tree. Single linkage does take clusters out of the tree. This is about as simple as you can imagine, and a really great thing about it is there are no parameters. You don't have to pick any thresholds, you don't have to pick any way to measure distances or anything. You got a data matrix and you just do it. But again, I have, if you want these charts, just come get them and you can see it. So sometimes it works. How many clusters are there? Well, this image you're going to see will tell you there are 4, and you'll see why. I wouldn't say there are 4 clusters there, but so what? If you just take these 20 points in R2 in random edge sequence order and make an image of them, this is what you get, and you can see nothing. Right? Certainly this data has structure, but it's not revealed by this image. But if you reorder it first, if you use that order, just look at this picture. You can see if I start right here and build a minimal spanning tree, it's going to connect all these points before it goes, right? It's going to jump here and connect all these points. Then it's going to jump here and connect all these points and finally down to here. You can just see how it works. That's the reason I like this, for example, because it produces exactly what you would expect it to. The big black square corresponds to the biggest cluster, and these 2 middle squares correspond to those 2 clusters, and the single pixel hanging out down here, right, corresponds to the single point. This is the whole idea of that, of iVAT, of asiVAT, SVAT, and so forth. Is to try to get an idea of structuring the data by creating an image that,
Something like this.
man, that's a long way away from home, man. Yeah, it could be. Open to the public.
No, it's not open to the public. Just discussion, right?
Yeah.
How it works. Same thing, right?
It's excellent. What a great poster this was. It was good fit. Okay. So, in this little example, you get this. So you want iris data. If you look at it in random order, it gives you this sort of a picture. If you look at it in that order, it sort of suggests that there are 2 clusters. Important, right? Not the right answer for every model, it's the right answer for most models. Even though people who are wrapped up in the labels of the iris data will say, no, there must be 3 clusters. That's false. Sometimes, however, how many clusters here? 3? 2? Hands up. I'm getting tired. Maybe halfway, yeah, well, halfway through. 2 clusters for sure. Right? If you do it in a direct way, this picture like it's on this poster. If you do it in that way, you get that thing. Well, what is that? That's who knows. Right? So, iVAT will fix this for most data sets. The word that I here stands for improve. And long was the guy who dug this up by giving, first, that is good, because for all kinds of data sets, object data, of course, you can turn into distance matrix using any norm you like, or from replacement or feature extraction on D, done using geodesic or all pair short path distance. And that's it. Okay, so let me just, this picture will tell you what that means. Here I have addresses or object INJs and object OIOJ, and in comes the data measure D, and there's a DIJ, the distance between OI and OJ. The dissimilarity, whatever it is, similarity, doesn't matter. So are there any other paths from I to J? Suppose there's a path like this, a different path, through the graph, thinking of the matrix T as, the edges of a graph on n vertices. I can find this path right here, but I find the biggest distance along this path is going to be this one right here, M1. Then I see, can I find another path? Well, there's one more path, and this is supposed to be the biggest distance. So accumulate all these distances from the paths right here, right? And I take the minimum of here there's 3, but I take the minimum of all those distances, and I just make that replacement. So here, it's going to be M1. So I'm going to take this value, let's say it's 305, and replace it with this value, which is 2.6 or whatever. Okay, so this is really feature extraction, and it's a kind of feature extraction done in spectral graph theory. Basis of this transformation lies in spectral graph theory, which is a great topic that's been around not so long. And this distance is perfect for us because it's a chain type of distance. It chains through the graph. So let's see what happens. Oh, so let me put this one up. Tim Havens and I published this paper just a couple years ago. So this is a recursive algorithm to produce the iVAT image. You don't have to use recursion. You can do it iteratively. But if you do it, again, it's user-friendly. If you do it iteratively, it's only cube, which is not good if it's a big data set. If you do it recursively, it cuts it down to 1 squared, which is still not so great, but better. So let's see what it does. I'm just going to put these up. Let's see what this is. How many clusters? The data set's at the top. Did you say 2? Okay. Okay. Here's that image. Here's that image, I of D star, and here's the iVAT image. See the difference? Right? How many clusters? That's right, 3. Like the VAT image, it's trying to get to 3, right? But the iVAT image certainly gets to 3. This is a good one. And when I was a graduate student, nobody thought you could even find those clusters by any method. And now it's kind of easy. Look at the iVAT image. Not only does it tell you exactly, look for 3 clusters, it says, but there's a big one, a medium size, and a little one. Let's put the rest of these up. You can't see that this is a segment of a helix. You can't see it just because of the way it's drawn. There are 3 segments. 4 straight lines. Boxes and stripes. So in every case, this is this is at least visually acute of any of the 5. But these iVAT images are much, much better than these VAT images. And they really reveal rather complicated structure in the data rather nicely. So now when I do this, and I do it a lot, I always use iVAT. I never use VAT. Ever. So I'll often forget to say iVAT in the rest of this talk, but you can think it. Here's some applications. This is a project with Jim Keller at the University of Missouri. So here's a time series of a patient. And this is 5 years worth of this patient's life. Lives in an eldercare facility. The brown is bed restlessness. So there's 2 sensors in this person's bedroom. A bed restlessness sensor and a bed motion sensor. All right? And these are just, this is the sum of the firings for each night. So, this is in a paper that's about to get published, I hope. Right now we're revising it, but I think it goes through. So there are 2 sensors. And this is no data here. This is the time when the patient was gone from the facility on a holiday. And this is the time when the patient had surgery. You'll see there is some activity even though the patient is known to be in the hospital. And the nurses conjecture the reason that there's this activity is because healthcare professionals going out of the room, clean the bathroom, what have you. So there was some activity. Hard to see why there would be any bed restlessness activity. So we clustered using single linkage, linguistic medoid prototypes. That's been a technical sounding term. So the prototypes are these statements. Delta T is a period of 15 minutes. Most 15-minute periods have low motion. A few 15-minute periods have medium restlessness and so forth. So this is self-explanatory. So this is a fuzzy system, actually. Okay, and this is the number of points in the cluster. You can see that there are 4 large clusters, and there's a couple of singletons at the other end. What that has to do with iVAT? Well, here's the iVAT image that we can see. So the iVAT image gives you a pretty clear depiction of the structure in the linguistic prototype set. Okay, much close to done. I'm more than halfway done. You guys are thinking, really? What can you do? Well, you can't believe what this is. Now, we worked on this for years and years and years on the assumption that we would always get square input data. And last summer when I was at Melbourne, University of Australia, started working with a couple of postdocs, I guess they were, that were interested in social network analysis, which has become a really big thing, social network analysis. And in social network analysis, most of the input matrices are not symmetric. So these kids said, well, you know, why do we use this? I mean, we have asymmetric input data. So I thought maybe we could just use the orthogonal projection theorem and get out of this. And in fact, you can easily prove this. I'm just going to show you that it's not, I hate to even call it a theorem because everybody knows it. So the symmetric matrices in ORN or vector subspace, everybody knows that, I guess, so there they are. And then it's easy to find an orthonormal basis of the symmetric matrices using, for example, Euclidean dot product from matrices. And here is the basis. There are n matrices that take care of the diagonal elements, and n times n minus 1 over 2 that take care of the off-diagonal elements. Remember, these are symmetric, so these are the basis elements. So now I have everything I need for the orthogonal projection theorem. Marius, I asked probably, when I stumbled onto this, I asked a half a dozen people in the math department in Melbourne if they'd ever seen this result, and they all said no. And so I started asking everybody I could think of, asking now, have you ever seen this result? All right, what I want to do is I want to project a non-symmetric matrix into this basis, into this subspace of symmetric matrices. And I'm going to use the orthogonal projection theorem. I have everything I need here. And there's the answer. A plus A transpose over 2 is the unique solution of the projection problem. And it minimizes, the square error between the input matrix A and every symmetric matrix Q that lies in Sn. So I have a picture over here. The residual error is A minus A transpose over 2. There's the picture of that. So prior to this, right now, I've been talking about symmetric data that live in this gray sheet, right? The symmetric matrices. Here's a matrix A that's asymmetric. And I'm just going to make the orthogonal projection of A down into the space. All right? And the orthogonal projection is this matrix P, A plus A transpose over 2, and the residual error, the length of it, is A minus A transpose over 2. Of course, if you add up P and R, you get A. So this is a kind of a cute little thing. I don't know, it's just I call it a fact in the paper world, but I was afraid to call it a theorem. I was afraid some math guy said, oh, big theorem guy. This is ASI, this is asymmetric iVAT on the iris data. So we start out with the Euclidean distance matrix and iris. And what we're going to do is we're going to take away some of the input values that are in the matrix DE and replace them with 1%, so that's 1, right? It's 150 points in this thing. But replace 1% of the off-diagonal entries with zeros. But look what happens for 5% and for 10%. This thing basically goes to, just disappeared. And Tim and I realized as we were doing this, the reason is that these imaging algorithms are driven by the smallest off-diagonal entries that you have. And if you just stick a bunch of zeros in there, it interprets them as value 0, of course, because they are, right? And it just degrades the hell out of your image. So to verify that, we just did it again, and instead of putting in zeros, we just randomly chose values in the interval 0, 7.1, which is the range of the iris data. So here's just put these up here because I got to keep going, right? There's 1% deterioration, 5%, 10%, even at 20%, it's not so bad. It's not so bad. So this just shows that this asiVAT thing can work for you, and it greatly expands the type of networks that you can look at. Here it is on boxes and stripes. I'll just put it up. Right? This is 1%, 5% still pretty good, 10% is kind of gone. It's hiding in here, 5% is gone. So. Okay. So here's an application. This is social network analysis. That's the application called Sampson's Monastery data. Turns out, I was thinking about this 2 days ago when I was over in Paphos, and I went to a monastery with zillion cats at it. How many people have ever been there?
Which
outside the village of Cal, they don't go over there.
Which monastery?
Eucalyptus? No, Neophytus.
I use nothing.
I use Neophytus. Your English is surely better than my Greek. I was thinking about the data set. This is a famous data set of social network analysis. But Sampson did this in 1968. This data has been around a long time, and people who do social network analysis, even though it's a small data set, love it. And you'll see why in a minute. So what is this data all about? So he went 5 different times. He went to each of the 18 monks, and he asked them, rate the top and bottom 3 brother monks over these 4 traits. And so, for example, he would ask the monk, list in order the 3 brothers you like the most, right? Or list in order the 3 brothers you like the least. So they did it for each of these 4 traits, right? Because they didn't do it for themselves, presumably. And Sampson asserted there were 3 groups of monks in this data set, and he called them the young Turks, the loyal opposition, and the outcasts. And for this reason, people who do social network analysis regard this as a labeled data set, ground truth. They say it's ground truth, but as we will see, that's hardly, there are just many, many papers about Sampson's monastery data, and the results are all over the map. So here is the monastery data right here. It's asymmetric, that's the reason it's in here. And this particular data set is the reason we invented asiVAT. So these are images of, this is the data now, this is not iVAT or asiVAT. These stacked images of the data set. This is the image of the symmetric projection of the data onto the set of symmetric matrices. But these, again, this is data. And here's the asiVAT image, so this asymmetric VAT. And asiVAT. So this image kind of crazy. Tim colored this image so that these 3 colors correspond to the 3 groups, that Sampson said were in there. And I don't know, this person right, this brother right here is not clear to me what's going on. This is what we would call a link between these 2 groups. And then there's these white ones, they're loyal opposition stuff. I don't know if this is lined up. Oh, this guy is supposed to this, I guess. And this one, and these 3 are loyal opposition. Anyway, about network access security. There's one paper about it, I have it if you want it, I didn't put it in my folder for you. Steve Bezdek gave me these charts. He worked for a company called CA, which means Computer Associates. Have you ever heard of it? It's a big company, actually. It has 13,000 employees worldwide. It's a $20 billion a year company. But their main products are software for mainframes, stuff like that. Anyway, wait to see this. He was a graduate student at Brown, and they got on, when I was over there, I was talking about Val all the time. He brought this up. This is really kind of cute. So in a company, you have users, right? And they have, the users get permission to access various databases, whatever, and they have roles inside the company. So that's what this is all about, is role-based access control. So these are his bullets. He says, you want to visualize clusters of user permissions, help with those role-based blah. All that method, clusters of user will show. So we've seen all that. Here's an organization where the roles are undefined. Here's an organization where the roles are much better defined. So this kind of weak for contrast diagonal block would indicate persons. Each of the rows and columns now represents a person whose role is possibly not well defined. A strong block would be clearly defined roles. And these would be used as unusual jump into part two. Nobody's getting up and rushing out of here. Just, you all think it's just kidding. Totally the bad, iVAT, and asiVAT are all limited without any problem. The numbers, of course, I know people have terabytes on a data set from the computer, so I think for 5,000 is nothing. One of the big pushes in clustering and in many other fields is to be able to scale these algorithms up so that they run on big data sets. Well, how big is big data? Who knows? I'm not going to me it's uninteresting to try to define how big the data set has to be called big data. For me, it means if you can't load it, it's big data. It's that simple, right? And no matter what computer you have, next year there'll be, even if you can load all the data sets today, next year there'll be data sets you can't load. So that's the reason scalable algorithms are interesting, important, and necessary, really. And so that's my definition of how big a field data is data you can't load. So what do we do? Remember now, I'm not talking about how to find clusters in it. I have a talk to that, but it's not this talk. In this talk, I'm simply saying, if you have a big data set, how can you get an idea of what to look for in it? In the same way using scalable VAT, that's what the S is, right? Or scalable iVAT or scalable asiVAT, that you would use for n small values of n. And there's nothing mysterious about this at all. We can't cluster data this big, we certainly can't look at it, so we have these, we build a sample. So I'll just put these up in a hurry. Here's a sample that I can VAT. I mean, it's big enough for me to make a VAT image over an iVAT image. And I have loadable, but I can't, there are many cases I can load, but they're too big to look at, make an image of. And I have really actually big data, which I can't load. So there are two sub cases, depending on whether I can load it or I can't VAT it, or whether I can't even load it. So if I can't make a VAT image of it, I can compare the image I get using real VAT to any approximation algorithm, but when I can't make an image using VAT, then I just have to believe that, I have to rest my case on examples for when I can make an image. So that's a problem they always have with referee section. Again, it's not so important that you understand this, the algorithm SVAT does have some parameters, and you'll see what these parameters are. The most important one is this one. So we're going to start out picking an index and just arbitrarily I'm going to pick what index? The first row of the matrix D. Right? So these are the values of the first row of the matrix D. That has to be the first row. You can pick any row you like. So here's what we're going to do. So we pick the first M1 as the first index. Here they're called prototype, but they're really indices. And then you get the distances to everything like this, and you find the next row in D, really, that's furthest away from the first, right? And you get that automatically when you find this one. You just keep doing it. And so the number of, just keep doing it until the number of indices is up to C prime, which is a parameter that you choose. Hopefully C prime is a little bigger than C. And we're always using the max and min rule. And once we have that, we can just get clusters in the nearest prototype rule, right? And that, since this is big data, you have to pay in and out to do it, but you can do it. You get the clusters. And then once you have the clusters, for each of the C prime clusters in the big data, we'll randomly sample NT times, NT is computed that way. So that what happens is you get something that looks like this. Okay, so now we just have a few samples from each of these clusters that we produce. And so here's the picture. So this is the big data matrix. It can be 100,000 by 100,000, it can be 1 million by 1 million, or 10 million by 10 million, right? And you have selected some rows and columns of it as the spectral ones using that initialization algorithm, and they produce a little seconds to make this image. Didn't have a bad image to compare it to, right? But this image does portray the structure of the data. And that's all you're trying to do. All you're trying to learn from these images is, should I look for 4 clusters? Should I look for 6 clusters? What should I do? I would not, based on this, say, go look for only 3 clusters. I would look for 2, 3, 4, 5, something like that. But I wouldn't look for 10. Okay, it's another approach that Leon Wong and the people in Australia developed. So this is a data set that had 3 million points in it, 3 times 10 to the 6. This is strictly only 30,000 of them. You can see there are 5 Gaussian clusters of various shapes. And here's the spec of that image. They went with 2,500 out of 3 million. Okay, so this is a pretty decent result, actually. Last one, here's some images from the Berkeley Image Segmentation Database. These are not huge images, but certainly they're too big for that. And the only feature we use for the segmentation is the distance between I and J. I, of course, is really IJ and KL or something like that. The intensity of the pixel, or the distance, it's just a difference in intensity. So here are the images. Here the iVAT image is 300 pixels taken from these images. And here are the segmentations produced by this scheme. So just for example, we can look at horses. So this is there are 3 clusters. There's the shadows of the horses along. So basically, this is a reasonable result. Bear in mind now, this is made with a very, very small subset of the actual data. The pictures, these pictures, segmentations is done on the whole image. And then I come to the last one. That sounds good, right? To me, this is the most interesting one, actually. Many people have rectangular relational data. This is becoming much, much more prevalent in data mining and machine learning communities than let's say 10 years ago. And what you, in this situation then, you'll have some set of row objects and a different set of column objects. And when you have the values in the matrix, so there's some relationship, a similarity, whatever, between a row object and a column object. For example, in the Netflix data, how many people know what that is? Some of you do. That's good. They get a fucking Taiwan because they never heard of Netflix. Well, so what? Netflix data, the rows of movies, and the columns are humans that are eating movies. And it's a giant data set. Really fun. There was a Netflix prize of $1 million won a few years ago, or some photos. We tried to do it. Some photos that tested Netflix's algorithm by 10%. Anyway, there are lots of data sets like this. And what many people don't realize, here's one of the most interesting. When halfway I did this work, I didn't realize it until we made this example right here. There are actually 4 kinds of clusters in such a data set. And here we have, we've represented row objects as circles and column objects as squares. And you can see there are some clusters that have only squares, right? Some clusters that have only circles, and some clusters that have both kinds. So there are 4 clustering problems associated with this. There are 3 clusters in the rows, 4 in the columns, 5 in the union, and 2 co-clusters. So this so-called co-clustering or bi-clustering, many people call this, is a big subfield bound clustering. Right? There are 2 clusters that have mixed row and column objects. So this has become an interesting thing. I didn't realize this until we did this work some years ago. And I think a lot of people still don't realize it. Now, how do we solve this problem? Our basic assumption was that the input data matrix, which is rectangular, was a small part of a bigger square matrix that capital N by capital N built in the following way. And the only data we have is this data right here. compute the row matrix, it's R by R, it's all artificial data, and you add it. You compute the column matrix, it's n by n, all artificial data, and you add it. Then now you have this big matrix, but this is input data and this is computed. So you have this matrix built this way, so you can VAT it. Now if it's too big to VAT, you SVAT, you SIVAT, whatever. And then once you've done that, you can unshuffle the array of indices for this big matrix, because you know that the first n minus go with the rows and the last n minus n go with the columns. So you just take the array, the indexing array that you've got and just unshuffle. And that's it. Use the unshuffle array to reorder R, which is what you're after. And the important thing to notice is, in this method, go about 1, R, the input data, is used in order to build this, the COVAT approach. That's important to see. So here are here's this data set that I was talking about. Here are the COVAT images. Just put them on fast. Okay. 3 clusters in the rows, 4 clusters in the columns, 5 clusters in the union, and 2 clusters, like 2 co-clusters in the rectangular input data. This is pretty nice. Of course, they're not a diagonal anymore because you don't have a diagonal. Right? So this is what you're after right here. All this stuff right here is generated sort of artificially in the sense that all 3 of these are made with computed data. It's kind of surprising that it works as well as it does, actually. Okay, here's a different example. Here are 4 magazines. Time magazine, National Geographic, this week's Smithsonian. I guess you're all familiar with these magazines. Here are some keywords, guns. Not funny, of course. Wars, lakes, seas, singers, dancers, and so forth. This is a little data matrix that you would think of in information retrieval, for example, where you have, magazines and newspaper documents, as well as in keywords as column key phrases. So, for example, the similarity between Time magazine and bomb is 1. If you think of these co-occurrences of these words, similarity between National Geographic and Dancer is 0.1. So you have the similarity matrix. You can display the COVAT image of the rectangular. Just put them up fast. In the rows, then you have 2 clusters, 2 magazines go together. National Geographic, Smithsonian, Eldercare, Time, and Newsweek. Okay. In the columns, you have 3 clusters. These 2 are kind of dark, actually. Like seas and ums, dancers, singers, and celebrities, guns, war, and bombs. In the union, it's either 2 or R1 and min R, you try to enhance the structure that it sees. Well, it doesn't see any structure. So here's the structure that you get with COVAT 2, and you can see clearly, we call it just so you can see, you know, so these are upregulated and downregulated genes. Here's an image of the columns, the gene, and it matches quite well. Matches quite well with the image that you get. Here's a single linkage dendrogram of the 18 treatments, and here's COVAT 2 of the rows. The rows are a number of the 18 treatments. Don't ask me what the treatments are, they're all different, I guess, strengths and compositions of field global and serum. If no, I don't want to get in trouble. This is the 18 treatments, and this is I didn't talk about dendrograms. This is yet another way to visually represent clusters, single linkage clusters. So there are 3 treatment clusters. You can see them right here in this image. And there's one lone wolf that doesn't fit into any of them. Very large rectangular data. Okay. Always long. All we do for big rectangular data is exactly what we did for big square data. I'm just going to page these up. Rather than skip them, I'm just going to put them all. You do it just exactly what you think you would do. You do it for the rows, and you do it for the columns, and then you get a sample based on, right? You get a sample based on the 2 separations you make, and then you can do the big data set. This is the data set that I had just showed. So again, this extends COVAT 1 and 2. The S can be applied to anything. Then you can do this for huge rectangular data sets. Conclusions. Don't you just love to see that word, conclusion? So why? Okay. Okay, so there's really the VAT, an asymmetric VAT, there's iVAT and asymmetric iVAT, right? So there's 4 basic algorithms. They're all limited in size to about 5,000. Other than that, there's really no problem with them. Then they're scalable, and this little star means all of the above, right? I can scale any of those, and then there's no size limit. And then there's co of all of the above. There's COVAT, there's iVAT, and so forth, so both 1 and 2. And those can be used to estimate or take a guess on how many clusters you have, right? And you can do the S's on the O's. I think it may be perfect. Right? You can scale the rectangular ones. And so the big family of algorithms, there's a lot of work been done, and plenty more work to do. It's fun because it's easy. You know, when you're my age, you don't want stuff to be hard. You don't want to work too hard, you want easy problems, you want stuff that can work easy problems. You all want that, right? This is a great field because it's visual, you know, humans can interact. And I really like it a lot. I've spent a lot of time on it the last 10 years. So why should you do this? Ronald Fisher said this 90 years ago in his famous book, Statistical Methods for Research Work. Diagrams prove nothing, but they bring outstanding features readily to the eye. I believe that 100%. 100%. Much later, Glenn Edwards, also in the UK, Glenn I've known quite well, and this nice little book graphical technique from multivariate data, said visual methods should never be regarded exclusively. You should always use them with some sort of analytic method alongside. I also believe that. But I think these 2 quotes embody what you will do with visual. What is that thing? Oh, it's a phone. Looking at it backwards, I don't know, I thought it was a computer. And then there are some other reasons. Here's one that you might be interested in. I know most of you all electrical engineers. Well, this may or may not be be a reason that you're interested in, but this is a true statement. This was in 2008. RDI means reward dissimilarity limits, which in the bioinformatics gang, they're called